Good morning, students. Chapter 6 Work, Energy and Power. Yes, we will see some questions today. A spring of force constant K is kept in compressed condition between two blocks of masses small m and capital M on smooth surface as shown in figure. When spring is released, both blocks move in opposite direction. When spring attains its original position, both the blocks lose the contact with spring. Find the speeds of block while getting detached from spring. See what is question. It is initial condition. It is initial condition. A spring having force constant K is compressed between two blocks having masses M and capital M. Okay, like this. If we have these two blocks, spring is compressed like this. Okay, now if spring is released, obviously these two blocks will move in opposite direction. Okay, and when this spring attains its original position means no compression. Original position means no compression. Okay, so in that condition, these two blocks lose their contact with spring. And yes, we have to find the speeds of block while getting detached from the spring. Clear? Yes. What is compression of spring? We are assuming, okay, let initial compression of spring is x. Let initial compression of spring is x. So in initial condition, this spring is in compressed condition while these two blocks are stationary. Yes or no? In initial condition, spring is in compressed condition and these two blocks are at rest. Yes or no? Yes, it is. Okay, so let initial compression of spring is x. So yes, in initial condition, spring is compressed. And blocks are at rest. Clear about this? Now, when spring is released, what happens? Yes, when spring is released, obviously these two blocks will move in opposite direction. Yes or no? These two blocks will move in opposite direction. Okay, so yes, this block M and this another block having mass capital M, they both are moving in opposite direction. And when spring attains its original position, it loses the contact with blocks. See, when spring attains its original position, both the blocks lose contact with spring. So yes, it is final condition. Okay, here this spring is compressed. Now in this spring, there is no compression. Clear about this? Okay, so yes, it is final condition. Okay, when this spring attains its normal condition, means no compression, then find speeds of these two blocks. I am assuming that speed of this block is u and speed of this block is v. Okay, so yes, I am assuming in final condition that speeds are u and v respectively. Having small m mass, speed is u. Having capital M mass, speed is v. Clear about this? Okay, so yes, now we have to find what is u and what is v. Clear about this? Yes. Here have to find u and v. So yes, we have to find two variables u and v. So obviously we have to obtain two equations, and from that two equations we can easily find what is u and v. From these two equations we can easily find what is value of u and v. Clear about this? Okay, so yes, see how to find. First of all, in this condition I will apply law of conservation of momentum. Law of conservation linear momentum. According to law of conservation of linear momentum. According to law of conservation of linear momentum. Okay, that is total initial moment is equal to total final moment. That is Pi is equal to Pf. Pi is equal to it is Pf. Clear about this? Okay, Pi is equal to it is Pf. In initial condition, see these two blocks are at rest. Spring is compressed and blocks are rest. So these two blocks are in rest condition. In rest condition, yes or no? So what is total initial momentum? Total initial momentum is 0. Clear about this? In initial condition, these two blocks are at rest. So that velocity is 0. So that momentum also 0. So it is 0. Pf, final momentum. See, in final condition, this spring is not compressed. This block is moving with speed v in this direction. This block is moving with speed u in this direction. Yes or no? Then how to write? See, how to write? What is momentum of this? It is mv plus. What is momentum of this? It is mu. But see, this v and u, they are in opposite direction. So how to write this? 0 is equal to mv minus mu. It is vector relation. So it is mv minus mu. Why minus sign? Because this v and u, they are in opposite direction. So yes, if you take mu this side, mu is equal to mv. So now make u as subject, then it is mv upon m. Equation number 1. U is equal to it is mv upon m. So it is first equation. Okay. Now as we have to find what is speed after we have to find speed after the spring is released. Okay. So yes, first equation according to law of conservation of momentum. Now how to obtain second equation? How to find this u and v? Then we will apply law of conservation of energy. See, according to law of conservation of energy. Law of conservation of energy. Total initial energy is equal to total final energy. Total initial energy is equal to total final energy. Total initial energy is equal to total final energy. See, initial condition, a spring which is in compressed. Okay, now see, total initial energy is equal to total final energy. How to write equation? Initially, this spring is only compressed. Yes or no? These two blocks are at rest. So what is energy of this spring? That is half kx square is equal to final condition. This spring is not compressed, so no potential energy in this spring. But these two blocks are moving. As blocks are moving, they have kinetic energy. And see, for this block, it is half capital M v square plus for this block it is half small m u square. Clear about this? Okay. So see, this half and half cut. Again, initially spring is only compressed. These two blocks are rest. So initial energy is of energy of spring, and finally we will have energies of these two blocks. Now kx square is equal to capital M v square plus small m. Yes. What is value of u square? Here is u. U is equal to mv mv upon m. U is equal to this mv upon m. So I will take square of this. So it is m square v square, capital M square v square upon small m. Upon small m. Clear about this? Kx square is equal to capital M, capital V whole square plus m u square. Now put value of u. So yes, you will get this m cut. Okay, and yes, this m cut. This m. Okay, so yes, here it is half mv square. Yes, here it is m square. Here it is m square. So 1 m cut, 1 m cut. Now how to simplify this? See, k x square is equal to, if I am taking b square as common, then in bracket it is m, only m, plus here it is m square upon m, and here it is b square. Simple, yes or no? Yes. Here from this equation, here you have to find, here you have to take b square as common. Also you can take m as common. Yes, also you can take m as common. So if we take m v square common, m v square, capital M v square, then capital M v square common. In bracket it is only 1 plus here capital M v square common. So here it is only 1 capital M, and in denominator it is small m. Okay, so yes, k x square is equal to m v square. In bracket, if I simplify this, it is small m plus capital M divided by small m. Now I will make this v square as subject. Then if you make this v square as subject, this m, it will come in numerator, that is km x square, divided by this m in denominator, and here it is small m plus capital M is equal to v square. Clear about this? So yes, therefore v is equal to, we have to take square root on both sides, is equal to, it is kn x square upon capital M small m plus capital M. It is equation of v. Clear about this? Yes, it is equation of v. V is equal to under root k m x square upon capital M plus m. What we have to do? According to law of conservation of energy, just you have to put value of u and you have to simplify this. Clear about this? So yes, it is equation of v. Now you have to find what is equation of u. Then how to find value of u? U is equal to, it is capital M upon small m into v. So here it is capital M upon small m into v. V means this equation, that is k m x square upon capital M small m plus capital M. Okay. Now if I take this capital M upon small m inside square root, then it becomes a square. You know that under root 4 is equal to, it is 2. Yes or no? Under root 4 is equal to, it is 2. Yes or no? Under root 4 is equal to, it is 2. But if I take this in reverse condition, it will be is under root 4. 2 square. Here it will become 2 square. So whenever we take this m upon m inside bracket, inside root, it will become square. How? See, here it is. Under m upon m. So I can write like this, m square upon m square. K m x square upon k m x square upon capital M plus n. Clear about this? So see, this small m cut. One capital M plus. So what is equation of u? U is equal to under root. K capital M x square. K capital M x square divided by small m and m plus m. So yes, here it is equation of u. Clear about this? So see, observe these two equations of v and u. K x square, small m and capital M. Clear about this? Denominator, capital M, here it is small m, and it is m plus n, here it is m plus n. Okay, so yes, you have to obtain these two equations of V and U. Okay, what is speed? What is speed of these two blocks after the spring is released? Clear about this? Now we will see next questions. Now next question is, if linear momentum of body is increased by 1%, its kinetic energy increases by blank percentage. See how to find such questions. First of all, linear momentum of body is increased by 1%, its kinetic energy increases by which percentage? So first of all, you have to obtain relation between these two quantities. One quantity is linear momentum. One quantity is linear momentum denoted by P, and another is kinetic energy. Kinetic energy, that is K. So what is relation between these two quantities? Yes, we know kinetic energy K is equal to, it is half mv square. If I multiply and divide by m, multiply and divide by m square plus square, it will become p square. So it is p square upon 2m. K is equal to p square upon 2m. This 2 is constant. 2 is constant. Mass is always constant. So what is relation between K and P? K is proportional to p square. K is proportional to p square. Clear about this? K is proportional to p square. Now, see here, if linear momentum of body is increased by 1%, means there is a small change. There is a small change. If linear momentum of body is increased by 1%, then yes, there is a small change. You have to find kinetic energy. Then see what is matter. Here it is. Here it is. For small changes. Write equation of K. That is K is equal to p square upon 2. What is method? See here. K. Here you have to write as dk upon K. That is change in kinetic energy upon K. Now, change in kinetic energy. Kinetic energy depends on 2, that is constant. Mass is also constant. Is equal to kinetic energy change when momentum is changed. Then see how to write this p square. It is 2 dp upon p. It is 2 dp upon p. It is 2 dp upon p. That is change in momentum. That is change in linear momentum. Now if I multiply this equation on both sides, then dk upon k into 100 is equal to 2 dp upon p into 100. It is how to find percentage. Change upon original into 100. Change upon original into 100. See, linear momentum of body is increased by 1%. So this 1% is answer of, this 1% is answer of dp upon p into 100 is equal to 1%. Is equal to 1%. And you have to find kinetic energy increases by, means you have to find dk upon k into 100 is equal to question mark. Is equal to question mark. So first of all, you have to understand question. First of all, you have to understand question. Okay, yes, change in momentum is given 1%. So what is change in kinetic energy? So yes, K is equal to p square upon 2m. This kinetic energy only depends on this momentum. This 2m is constant. So yes, also from this equation you can write K dk upon k is equal to this 2 dp upon p. It is 2 dp upon p. Clear about this? Clear about this? Okay, so yes, it is for change. Now dk upon k into 100 is equal to 2 dp upon p into 100. So yes, change in kinetic energy dk upon k into 100 is equal to 2 dp upon p into 100. Yes, you are given. It is 1%. It is 1%. So your answer is 2%. Okay, if change in linear momentum is increased by 1%, then what is change in kinetic energy? Change in kinetic energy is 2%. Change in kinetic energy is 2%. Clear about this? Now, if change is large, for example, if I repeat the same question, okay, if linear momentum, if linear momentum of body, if linear momentum of body is increased by 100%, its kinetic energy, increases by blank percentage. Again same question, but see here the change is very small, 1%, while here change is 100%. So there is another method. You cannot use this method. This method is only used for small changes. This method is used for only small changes. Then for large change, what is method? See here. Linear momentum of body is increased by 100%. So I am assuming that initial linear momentum P1 is equal to P. Clear about this? I have assumed. So final momentum P2 is equal. Now understand meaning of, if linear momentum of body is increased by 100%, it's increased by 100%, means initial is P and it is increased by 100% of P. It is increased by 100% of P. See how to write this equation. Okay, linear momentum of body is increased by 100%, is increased by 100. Initial momentum is P. Now is increased, means it is plus 100% of P. Then how to find it? See, is equal to, it is P plus, how to find percentage? 100 divided by 100 into P. So 100 upon 100 cut, so is equal to, it is to P. And yes, we know that 100% change means double. Okay, so yes, here linear momentum is double. Then what is change in kinetic energy? Yes, what is relation between kinetic energy and momentum? K is proportional to P square. So here K2 is proportional to P2 square, while K1 is proportional to P1 square. So if I am taking the ratio, then K2 upon K1 is equal to, here it is P2 upon P1 whole square. Clear about this? Yes, I can write the whole square. So is equal to, it is P2, it is 2P, while P1 it is P cut, and here it is square, so here it is 4. So K2 is equal to 4K1, means kinetic energy becomes 4 times. Kinetic energy becomes 4 times, but we have to find what is percentage change. We have to find what is percentage change. Then how to find this percentage change? How to find this percentage change? See, we have equation. Okay, percentage change is equal to change upon original value into 100. Change upon original value into 100. It is equation. How to find percentage change? It is equation. A change upon original into 100. Then yes, percentage change in kinetic energy is equal to change in kinetic energy delta K upon initial kinetic energy, that is K1, and here it is 100. Clear about this? So yes, delta K means change in kinetic energy. Change in kinetic energy means it is final kinetic energy minus initial kinetic energy upon initial, means the original kinetic energy, and here it is into 100. So is equal to, what is value of K2? K2 is 4K1. It is 4K1 minus, here it is K1 upon, here it is K1 into 100 is equal to, it is 3K1 upon K1 into 100. So here it is K1 cut, and here it is called 300%. Here it is called 300%. Clear about this? So yes, it is one method, okay, how to find percentage change. How to find percentage change. Yes, you will be given two quantities. One quantity linear momentum is increased or decreased. then you have to find what is change in another quantity. So first of all, linear momentum of body is increased by 100%. So you have to assume initial. As it is increased, so here you have to write plus. Here you have to write plus. Okay, and here it is 2p. K is proportional to p square. How to write this equation? You have to find K2. Then to find percentage change, it is equation. That is percentage change is equal to change upon original into 100. Put value, you will get your answer. You will get your answer. Yes, you have to calculate one question. That is, if linear momentum of body is increased by 50%, if linear momentum of body is increased by 50%, then what is change in kinetic energy? What is change in kinetic energy? Then you have to find in the same manner. And yes, your answer you have to write in comment box. Okay?